Okay, I would like to introduce our student speaker for this session. We have Mohit Prashant from Nanyang Technological University, presenting his paper entitled Adversarial Input Masking. You have 20 minutes to conclude your presentation, and then we'll have me. You can now share your screen, and good luck.
Sorry. Can everyone see my screen?
Yeah, we can see.
Perfect. In that case, I will begin. Thank you everyone for attending. My presentation today will be about adversarial input masking. So the aim of the study is to improve image classifier performance through adversarial training. And before I move on to what adversarial input masking is, I'm going to talk a little bit about masking. So masking is the addition of noise to allow to obscure information. So something you might be familiar with is dropout, which is a classical example of masking. And just to see it visually, when masking an image, you might want to add a random mask, and your result would look something like this. It's a straightforward addition. And there are a couple of reasons why you might do this. So firstly, it desensitizes the network to noise, thereby increasing our classifier robustness, which just means that it would be that any additional perturbation would be less likely to change the output of our classification. Secondly, masking regularizes the network, thereby dropping reliance on unnecessary information, allowing it to perform better on unseen data. So as the title adversarial masking might imply, we're basing this on adversarial training. And just to brief you quickly on this as well, two networks work against each other to min-max a particular objective. Because when min-maxing, you are mutually challenging each other, and you might be able to learn the target concept a bit better. A classical example of this are generative adversarial networks. So, of course, as I mentioned, adversarial masking is a form of adversarial training, wherein the classifier aims to maximize the probability of a correct prediction, and the mask generator attempts to minimize this. So the rationale for the approach of this study was that producing targeted noise would better be able to challenge the classifier and thereby increase performance on unseen data. Secondly, as mentioned earlier, masking reduces overfitting, but adversarially targeting features causes us to reduce overfitting at a feature level. There's a few reasons for this. So firstly, by adding noise resembling decoy features, you'd be able to reduce overfitting for more handwriting resembling noise. Secondly, we'd be able to reduce dependency on certain features that might not provide enough information to help classify within certain labels. And lastly, we'd be able to increase holistic feature dependency. That is, we'd be able to take into account all aspects of an image before providing a label. And lastly, of course, we'd be able to artificially increase the training pool with ambiguous cases. By ambiguous cases, I mean boundary cases that have ambiguous labels. Some examples of these. These were extracted from the MNIST dataset, and as you can see why they'd be considered boundary cases. So now when structuring adversarial training for classification, there's a few things you need to keep in mind. The architecture for adversarial training consists of two subnetworks, a classifier and a mask generator. The mask generator masks the input sent to the classifier, and the classifier tries its best to make the correct prediction. So our training architecture visually would look something like this. We'd have a mask generator and a classifier. We'd pass our training input into the mask generator, which would then yield, of course, a mask, which we could then add to our training input as shown previously. This would then be passed to the classifier, and our output prediction could be used to calculate loss. Now, our classifier would aim to minimize this loss, and our mask generator would aim to maximize this. So before moving on to the results of the experiment, I'd like to talk a little bit about our loss functions used. So firstly, our classifier classically minimizes the difference between our output label and input label. And our mask generator does the opposite. However, I'd like to keep in mind that prior to classification, we'd be transforming this input. So you can consider this as C of G of X. And based on experiments, as well as the results of the 2014 GAN paper, the best form for the loss function here would be the logarithm of this. So now, of course, there are a lot of failures you might encounter during the learning process. And I'd like to talk a little bit about these. So some of the failures that the mask generator can encounter are firstly, whitewashing, and secondly, generator collapse. These were the most frequently noticed. And I have included the solutions to these as well. So just to give you an overview of what whitewashing is, when you begin your training process, your mask might resemble something like random noise. However, our mask generator is incentivized to maximize the entropy of input. And what this means is that it is designed to reduce the amount of information the classifier receives, making it as hard as possible. So by the time it converges, we might get something like this. And of course, our classifier can read nothing from this and instantly loses. So we have to penalize this. We need to penalize it to prevent high entropy masking. I attempted a couple of methods, and based on those, the best one is to sample our generated mask, construct a secondary mask from it. So this is our uniform mask. And we're aiming to maximize the element-wise relative entropy between these masks. As a penalty term, this can look something like a Gale divergence between these two. And thereby we'd be penalizing the closeness of these two and how representative they are of each other. Secondly, generator collapse. So to summarize it briefly, it's when our mask generator gets lazy and collapses. So when our mask generator starts overfitting, regardless of the input, it'll start producing the same mask. This is an observed phenomenon even in GANs. And it looks a bit like this. So regardless of the input, we have the same mask. So obviously, since we're aiming to uniquely target and attack inputs, this is unacceptable. So again, we have to penalize this similarly. One method of doing so is to maximize, again, the element-wise relative entropy between these masks. So what you might do is you'd save your previous mask and construct a Gale divergence loss between your current mask and your previous one, thereby maximizing any difference between the two. So this is, again, as I mentioned, a Gale divergence term. And to revisit the loss functions, our mask generator loss function would look something like this now. We'd attempt to maximize this and thereby reduce any error of generator collapse or whitewashing. So I think this is the section that we've been waiting for, the results. I'd like to talk a bit about the methodology involved. So this was a simple comparison between three models. Firstly, a vanilla convolutional neural network, as well as a convolutional network that was masked using a Gaussian mask, and our adversarially trained convolutional neural network. The experiment parameters were 200 training samples over 50 trials, and each model was trained till the point of overfit. So this is these are the results from a single trial. So we can see that the accuracy over time of the adversarially trained network is far higher than our base neural network and slightly higher than our Gaussian neural network. So just to give you figures over the course of the 50 trials, within one standard deviation of the mean, we would see something like 84 to 87% for adversarial mask versus 82 to 85% for a Gaussian mask, and 72 to 77% for a convolutional neural network. Now, a hypothesis test was conducted at a 5% significance level, and it was confirmed that our adversarial mask had better performance. For some further, sorry, let me repeat myself. Some further comparisons that we might want to look at are training time, as well as training stability and overfitting. So now, as observed in our previous slide, adversarially masking our inputs required significantly more time to train, but it did yield some improvements in performance. However, training stability and overfitting, what we can see is that our adversarially masked network has a tendency not to overfit. At least it was not observed within the 5,000 epochs for that it was trained on per trial. Whereas our baseline CNN as well as our Gaussian mask show some degree of overfitting within the validation loss. But I'd also like you to know that our training loss for the adversarial mask has a high degree of fluctuation. To give you some insight to what our mask samples might look like, we'd see a lot of ones being misrepresented as sevens after being masked. We'd see a lot of eights showing up, either from zeros being masked, or twos being masked, or sixes being masked, or fives being masked. But as well as this, we'd also see a lot of other more ambiguous looking masks, like the example of 6 on the top left. Some practical applications now. Potentially, we might see applications of adversarial training for classification within autonomous vehicles, as well as within medical diagnosis. Basically, within safety critical tasks, where training time is not a consideration when compared with minor performance increases. But alternative uses might also be penetration testing, as well as natural language processing with some tweaks to the model. Basically, any classification-based problem. Before I end this presentation, I'd like to leave everyone with some food for thought. And that is, if a masked input looks like it belongs to a class not corresponding with its label, what should the classifier predict? So if we have a 1 that's been masked to look exactly like a 7, it would be an error to predict 1 as opposed to 7. And we might see this in more complicated data sets, with certain features being paired with the wrong labels. A temporary solution to this is to place a dropout on the mask prior to adding it. And this, of course, reduces the impact of the mask in adversarially attacking the classifier. Some future work that I might consider on this is working with more complex data, resolving misclassification issues, as mentioned previously, working with larger data sets, and improving the generated loss function. This will be an ongoing process, but I hope to see some results from this. Thank you. My presentation is concluded. If anyone has any questions, I'd be glad to take them now.
Thank you, Mohit, for your presentation. So we open the floor to questions. We have 10 minutes for questions. So if anyone have any questions, please ask in the Zoom chat, or you can also ask through Hoover. So, yeah. Okay, Mohit, I have a question. So can you elaborate a little bit on what are the reasons that the rate of convergence of your adversarial network is a little slower than the other ones? Because you see, like it does cross over the Gaussian towards the end, but it takes its own sweet time. So any particular reasons why it happens?
Sure. So one reason I might see this is because, of course, it's being adversarially targeted. So what that means is it'll learn a lot slower as the masks being generated are generated in such a way to prevent any, to maximize uncertainty. That means that the classifier will learn a lot slower.
Okay. And does this have any implications if this networking is being used in the real life setting?
Yeah, of course. So I haven't tested this out with more complicated data sets yet, but I'm expecting that training time would increase by a lot as opposed to conventional nets. Now, this might be an issue for smaller, more localized tasks, but the increase in training performance is vastly outweighed by the increase in performance. The increase in training time is vastly outweighed by the increase in training performance on more safety critical tasks.
All right, thank you, Mohit. So let's wait a little more for more questions by the audience.
Sure.
I see a question from Mac. So what are the major problems or roadblocks that you faced while doing your research?
Hi, sure. So the major problem faced while doing this was actually constructing the loss function for the generator. So in order to construct the loss function, I mentioned that there were a few issues with the learning process. So that was whitewashing as well as generator collapse. In order to resolve these, more classical approaches include unrolling the generator. So that is resolving the generator into a more recurrent neural network like architecture. And this is computationally expensive. So it slows down training time even further, as well as increasing CPU utilization. So it's practically not runnable on my computer.
Okay, thank you, Mohit. Let's wait for a little more time. Hey, so let's say you've provided any sort of resources to continue your project and develop further on it. So what resources are you looking for? You look for better systems, or a better data warehouse, or what is your highest priority when if you want to move forward with this project?
So my first priority is to apply it to larger as well as more complicated data sets. Because
Okay.
of course the degree of feature masking as well as feature generation will be a lot more
Okay.
yeah, it'll be a lot more complicated. And again, I might have to make some tweaks to the way the generator is structured.
All right. And what steps would you take to get this data?
So some data sets that I've been looking at are the new scenes data set, as well as fashion MNIST, which contain a lot more which contain more overlapping features between individual training labels as well as more classes in general.
Okay. All right. I think that's all from my side, and seeing that there are no more questions, we will end the Q&A session. And so thank you everyone for attending this session by Mohit, and thank you Mohit for presenting your project. It was great to know about the work that you're doing. So we have our next guest presentation by Professor Michael Woodridge on the topic understanding equilibrium properties of multi-agent systems. So I'd like to invite all of you to watch the video and get to know more about what Professor Michael Woodridge is up to, and it starts at 3:45 p.m. Singapore Standard Time. So looking forward to seeing you there. We also have another panel discussion that you can take part at 4:30 p.m. So thank you.